Buenas tardes a todos. Es un gusto para mí tener aquí a Remix. Ahora aquí, él es un investigador que se encuentra en el departamento de Astronomía en la Universidad de Guanajuato, cerca de nosotros. Es la primera vez que yo conozco a Remix. Es interesante, él tiene ya 15 años trabajando ahí en Guanajuato. Lo había conocido personalmente. Él, pues, él es un poquito de su semblanza. Me preparó. Estudié en la Universidad de Hamburgo, en Alemania, del 2001 al 2006. Hizo su doctorado y desde la maestría pues ha estado trabajando, ¿no? Por ahí, después de sus estudios, pues se quedó 2 años más en el Observatorio de Hamburgo trabajando como postdoc. Y por ahí, en el 2012, pues ya llegó a ser profesor aquí en el Instituto en el Departamento de Astronomía en la Universidad de Guanajuato, principalmente trabajando en el área de física estelar. Yo a David lo conocí por mi postdoc, Finder. Ha estado trabajando mucho con los modelos que él les va a presentar sobre las estrellas. Principalmente nosotros trabajamos en Chromospheres con postdoc, y él fue uno de los expertos en este programa que se llama Phoenix, ¿no? Sobre los modelos, que es muy importante. Entonces hemos estado colaborando con él. Y pues es un placer tenerlo por aquí, es bueno conocerte de cara, ¿no? Y verlo, pues adelante. Muchas gracias por sí.
Gracias. Okay, so I'm going to talk in English. My talk will mainly about the Phoenix code, which I have been working with since my start in astrophysics, basically. So I'm going to present an overview. So I will first give a short motivation introduction into the topic so that everyone has an idea why is it interesting to model the atmospheres of stars. Then I'm going to present mainly the Phoenix code. There are a lot of other codes that model atmospheres or do at least radiative transfer. And then I'll present briefly the necessary physics that you need, at least for a normal star, to model the atmosphere. That you could actually give at least half of a course, or if not a whole course, on all of the physics that you need to model the atmosphere. I don't have that much time, so I will just briefly and quickly go through all of the physics, but just mentioning the essential parts of it. And I will give some examples of what I have been working with, and also what is possible with the Phoenix code. So I worked in my master in my PhD with supernovae. After coming to Mexico, I left this a bit behind, did not work on supernovae anymore, but later I started to use again what I did in my PhD. I will come to that later. So at the end, I'm going to talk a bit about what I'm currently doing, among other things, which is modeling, or try to model, the chromospheres of stars, which are, if you want, part of the atmosphere, but not a part that Phoenix normally can do or can model. Okay, so, yeah, slow. Okay, so a bit about the motivation. So we as astrophysicists have one big problem. We cannot just go to our objects of interest and measure, do experiments or anything. We have to rely on what we actually see. Nowadays we have telescopes, so we're not only what we see with our eyes, but only see, let's say, with the telescope. So the electromagnetic spectrum going from X-rays, gamma rays, up or down to however you want, to radio. So when we do this with stars, already taking a picture of a lot of stars, we see that they must have different properties, as there are stars which are blue, others which are red. So they probably have different properties. So the question is, how do we get, since we cannot go there and actually measure anything, how can we get information about our objects of interest in this case, in my case, which are the stars. That we come to what is stellar astrophysics. So what we can observe, I said it, the whole electromagnetic spectrum, so we can observe spectra. And if we take a look at a spectrum, I know this is not really scientific here, but I think it's a nice picture. So if you take a look at the spectrum, you see that there are a lot of lines in stellar spectra. You have absorption lines usually. You see that with these absorption lines. And the question is, do we get anything out of the spectra? And actually, there's a lot of information hidden in the spectrum. So you can get ideas about the temperatures, you can get ideas about gravity, about densities, about pressures, important also the abundances. You can check if there are any molecules, even if there's dust. All this has an effect on the spectrum. The question is more, how do we get the information out of the spectrum? So just by looking at the spectrum, well, if experience, you can get something out of it, but normally you have no idea what do I really see there. So the abundances and also the temperatures, you can get a bit from the color, for example, and of certain lines that you can associate to elements. You have to have an idea about atomic physics, actually, so that you can then connect specific spectral lines to elements, and with that measure then abundances and temperatures. So this is one way, studying a lot of spectra and trying to, by looking at how strong are certain lines, have an idea about temperature, have an idea about the abundances and many other physical parameters. So this is what astronomers have been doing for since spectra were available. The other option is, and that is what I'm doing, is try to model the whole atmosphere, which then gives you as a result the spectrum that this model star would emit, and compare your model with the observations. And then by playing around with your model, changing the properties, you will get a better idea. Or the idea, of course, is at the end, have a perfect match with the observations, and then you know absolutely everything about the star, about the atmosphere. Of course, that does not work that easy, but it works quite well. So that is the idea that we want to do. So in order to do this, there are many codes. Most of them do radiative transfer. They include some physics. There are usually for specific objects. There are very good codes which are including all the physics that you need in order to model this type of star or stellar-like object. And but then Phoenix is a code that really tries to model the whole physics of the atmosphere. So it's not just a radiative transfer code, it's really a model of the complete atmosphere. And Phoenix, I will not say that it's the best code, it's, I would say, the most complete code, because it includes a lot of physics, and you can use it for brown dwarfs, for novae, supernovae, for neutron stars, for normal stars as well. Even you can model disks, you can do a lot of things with Phoenix, so it's very versatile in that sense. So my idea here is to present about, talk about Phoenix, so that you get an idea about what Phoenix is, can do, and all the physics that you need in order to make it run. The code has already quite some history, so it was started, the development of Phoenix was started in the 90s with the main father of the code, Peter Hausstedt, who in his PhD started to model actually spectra of novae, and then later amplified his code to stars and nowadays to more. There are a lot of collaborators who work on the development of the code, and I was actually one of them. So Peter Hausstedt, he works in Hamburg, the University of Hamburg, and I was his master student and PhD student. So I also contributed to the code. And as I said, after then coming to Mexico, I kind of did a lot of other things, but now I'm a bit coming back to the code. So the code is written in Fortran. It's parallelized, which means you can use it on a supercomputer, and it will be a lot faster than just on your small laptop, for example. Okay, so I will go a bit into the details. So what do we need if we want to model a star or any stellar-like object? So, first of all, you have to decide how complex you want to have your model. And Phoenix, and the good thing about stars are mostly just one-dimensional objects. Before he decided to divide the star into plane parallel layers, that you can do if the atmosphere is small compared to the radius. Then the atmosphere is like or similar to just plain parallel layers. If you are doing larger or stars that have a larger atmosphere, like giants, for example, you cannot do this anymore. Then you can, what you have to do is to divide your star into spheres, and there you assume that all your physical quantities just depend on where you are distance from the center in that. So that's what Phoenix is doing. Not anymore, that's already a 3D code, I will come to that later. But the first was to assume that if a star, if you divide it into spherical symmetric layers. Then you have to say to the code, okay, this is my given density structure. Usually it's given, and the abundances as well. So for a star, usually you start with, I don't know, solar abundances, so it's a good example. And then the first thing is, of course, it includes, let's say, the basic stellar physics of constructing a star. So you have hydrostatic equilibrium, or if your star is, for some reason, or your object, expanding or contracting, you can also include hydrodynamic equilibrium. Then you have to see how does the energy travel from the center. We know there's the energy source to the outside, and that's done by either radiation or convection. And that point of radiation is the most complex, and actually also the one that we're interested in, since we want to have a spectrum with radiation, so the radiation transport will give us actually, as a result, a spectrum. This is more or less how Phoenix work. I will not go into too much detail. So you give it a lot of input parameters, for example, for a star, what is the effective temperature, what is the mass, luminosity, something like this. It will then, by having as input also the density structure, first solve the equation of state and tell you what are the pressures, what are the ionization stages of every element that you have in your star. Based on that, you can then calculate all the opacities, which can be line opacities, continuum opacities, molecular opacities, if you have it, even dust. And then you solve the radiative transfer problem. You get then, as a result, a radiation field. And that radiation field is then your output. And then you have to ask one question: is the star in radiative equilibrium? Radiative equilibrium means that all the energy that comes from the center and passes through the atmosphere is really the same in every layer, so that there's no energy generated nor energy lost. Usually, if you solve all this, you will see that there are some layers that have a higher energy throughput, a higher energy flux, so you have to lower a bit the temperature. So you have to correct the temperature of every layer, so that after doing a lot of these iterations, you end up with a complete consistent model of the atmosphere, where you have radiative equilibrium, so the energy that comes from below passes through every layer and it's everywhere the same. And then you have also, as a result, since you then know the radiation field, you have also the synthetic spectrum. Now, going a bit Into details, well, I guess we all know the radiative transfer equation, a very simple one that you see in class. The one that Phoenix solves is a bit more complex. So this is the radiative transfer equation that Phoenix solves. It's the spherically symmetric that I explained, special relativistic radiative transfer equation. So it includes also objects where the envelopes are expanding. So this is usually supernovae. So supernovae can expand up to 10% of the speed of light. So then you need special relativity, and this is also included in the radiative transfer equation that Phoenix is solving. So this is here just an example. I will not go into details. But Phoenix does, since we want to have a spectrum, you have to solve the radiative transfer equation actually for every wavelength point. So if you want to have a full spectrum with a good resolution of the spectral lines, you have to solve the radiative transfer equation like this, depending on your resolution. Could be up to 100 or even a million times if you want to have a very high resolution spectrum that covers a lot of the radiative, the spectrum of your star, for example. So you divide your spectrum into wavelength points, and Phoenix solves every wavelength point, solving the radiative transfer equation. For that, of course, we need the absorption and emission coefficients, or the source function, and for that we need the opacities, which is on the next slide. So, what are the opacities that are included in Phoenix? Just to give you an idea. Of course, very simple, all the opacities of atoms and ions. So you have to really know how many ions of every element you have. Then you include the free opacities, which are usually fitting formulas, relatively easy, bound-free, so by ionization and recombination. And the most complex, which are the bound, which is all of the specific lines that you have in your spectrum.
Can I ask a question?
Yes.
Do you go all the way up to iron?
Yes.
In the transition, okay.
Yeah. So this is just so the bound, for example, have in total about 80 million lines, which are included in the code. So the code is not only the code; you have a large database of atomic data for the atomic lines. And if we go to the molecules, I don't know the exact number, but it's above 1 billion of lines that are in a database for the Phoenix code. So all the opacities of the lines are actually there. Okay, so it includes scattering for some types of stars, especially with lower temperatures. We have very broad line profiles, and these are special line profiles which are also included in the Phoenix code, so that you can also model like grounders or something that have these very broad line profiles. It also includes line broadening, so by Doppler, by pressure broadening, all of this is also included in the code, and of course affects the opacities. And as I said, molecules are there. And there's also a model that considers the opacities of dust, so that it can really go down to very low effective temperatures when you model your stars, or brown dwarfs, or even go to planetary or Jupiter's atmosphere or something. Okay, so it also solves the equation of state. As I said, it's actually a step before the opacities. So you need to know for your star the exact distribution of all the ionization stages and energy levels where your stars are in. Also, you need to include, if you have lower temperatures, the formation of molecules. So each element can form a molecule with the other, and then the element is, of course, away from having the atomic opacity. So it then has molecular opacity. So all of that we have to solve. So the equation of state, using only atoms, it's relatively simple to solve that, but now including molecules, and It even includes the formation of dust particles and of liquid states of some elements which are given a bit here above. All of this is included in the equation of state, which is again solved usually at the beginning when you have your abundances and the density structure. You solve for the given temperature, of course. You solve the Boltzmann equation, including molecules if necessary, and with that you can then have the whole distribution of, or the whole states of your elements, ionization and energy levels, as well as if it's in a liquid state or if there are any dust particles or molecules as well. Okay, a bit about LTE, which is local thermodynamic equilibrium. It means that you assume that your star or the atmosphere, every layer has, you can define a temperature, assign a temperature to it, and that temperature then gives you directly all of the ionization stages and the energy levels as well. That's very easy, and it actually is quite good assumption, more or less, for let's say, normal stars. So if we take here a look at, so the yellow is the solar spectrum, of course measured above our atmosphere, and you compare to the Planck functions, then you see that it more or less fits. So the assumption of LTE is actually usually a good assumption, depending on the type of object. Okay, then we go to the more complex case, which is non-LTE. Non-LTE just means that the assumption of LTE does not work. So you cannot assign to your layer a temperature, and the occupation numbers are not given just by the Boltzmann equation. So the question is then, how do we get the occupation number for each layer? And you do this by really solving the rate equation. So you have your radiation field, and the radiation field moves one electron up, or can move it down, and you really take a look at all of the connections, all of the transitions that are possible between the levels. And solve this. The only assumption that you do is statistical equilibrium, which means that these rates are not changing in time. So you have a state, are not Boltzmann, but they also do not change in time. So the whole environment is stable, if we want to say. In case of hydrogen, it's not that complicated. So hydrogen, maybe you have 10 levels or something. So you have, of course, a bit more transitions, but you can more or less solve this easily. Problem gets more problematic when you go to elements. This is just an example. Iron 2, for example, has 600 levels and over 13,000 possible transitions. So you have to solve the rate equation for those almost 14,000 transitions. That, of course, gets a bit complicated. And you have to do it, of course, by iteration. So you solve it, you change the occupation numbers, which then change, of course, the opacities. So you have to solve again the radiative transfer, which will change your rate equation, which will change again your occupation numbers, and so on. So you have to do several iterations with solving the rate equations until you get to a model that is consistent with NLT. And as I said, this is just one ionization state of many that you may have in your object. So doing non-LTE in terms of computation is really something quite difficult to do. Okay, forget something. And we have, of course, we do not have only the radiative rate, so not only the radiation field can change your occupation numbers, also collisions between the elements contribute to that. So you have to include both of it into the code when you want to solve your atmosphere, including properties of non-LTE. Okay, and then the code includes also some special physics depending on objects. So what you can do with it is you include expanding atmospheres, so that are not like a star not moving, so they are expanding, and you have to include the movement as well. It also includes a model where you can have irradiation, so some radiation from the outside that then has an effect on the atmosphere of the star. So these irradiated objects, which you have usually in binary systems, or even especially in exoplanets. So if you want to have the atmosphere of an exoplanet, it will be, of course, affected by the host star, which emits the light, its spectrum onto the exoplanet. The special line profiles I talked about in brown dwarfs. There is also a mode where general relativity is included, so you can model spectra of neutron stars, for example. There is also a module for the modeling of this. I have no really an idea how it works, but it kind of is a 2D extension, two-dimensional extension of the Phoenix code. And it works for this as well. I've never used it. You can include winds as well if you have, for example, massive stars or stars that have a wind. Okay, so that's very quick. So you can give a whole course of all of the physics that you really need there. And the question is, does it work? And here's a comparison between a Phoenix spectrum and the solar spectrum. Of course, the sun, we have a very good idea about, more or less a good idea about how the sun works, its abundances, and so on. So the code should give an almost perfect fit to the solar spectrum. And it actually kind of does it. You see that sometimes, for example here, there are lines in the code which are not in the spectrum. And I don't know if it's another case where you have the line
6517-ish.
So there you have the line in the spectrum, and it's not in the code. So usually the problem is the atomic data. No? I talked about 80 million atomic lines. Obviously, we have not really an idea about all of the properties of all of these 80 million lines. So that is one of the problems, for example. And of course, we have just 1D assumption. This, I guess, it's an LTE calculation, but again, not all of the elements you can include it. But anyway, in total, the code works and gives us quite good spectra, not only for the sun, which I show you as an example, but for many types of stars.
Excuse me, which is the theoretical spectrum?
That is the thin line.
Oh, okay.
Okay, then I'll quickly go through this. So now about 10 years or so, we actually started to work on a 3D code. Of course, it's still not complete. The problem is not really the code, but the computers, which are just too slow to solve the whole problem in 3D. Just to give you an idea, if you have the 1D code, you divide the atmosphere into 64 layers. For a normal star, if you have something more complex, 128 layers. If you do the same in 3D, so you divide your 3D star into 180, but you have now 3 dimensions, so it's to the power of 3. So you're talking about 70 million, he calls it voxels, volume elements. And if you then want to solve, to save just one scalar variable, for example, the temperature, you need at least 180 megabytes of memory. But here we're talking just the temperature. So if you have, for example, a velocity at 3 dimensions, so you're always at half of a gigabyte. If you're talking about the abundances, I said that it has about 80 elements, so 80 times this, you're at a few gigabytes. And if you then want to save all of the information about the ionization stages, you end up very quickly with even gigabytes up to terabytes of memory that you need while running the code. So that is something that is computationally very demanding. However, you can do very nice things with the 3D code. I'll just show you some examples. So these are very simple, so you can really have a picture So this is another example. This is taking a part of the star where other people with the hydrodynamics code have simulated convection, and then you put it into the Phoenix code, and it gives you how you would see this. Okay, I'll just quickly go through this. Now I come to an example of what I have been doing. So in my master's thesis, I started to work with type 1a supernovae. Okay. In the PhD, I had to, so this is just to show how a type 1a supernova looks like. You have a white dwarf here at the center, and a companion star which transfers mass onto the white dwarf. And at some point, the white dwarf says, okay, I'm too heavy, I'll just explode. And the whole star disrupts, and you see this as a type 1a supernova. So, one well-known property of type 1a supernova is that their light curves are not really the same, but you can correct them. You see that less luminous supernovae have a steeper decline, while the brighter ones have a slower decline. If you correct this, you get one perfect light curve. So 1a supernovae are used for measuring distances. We know in cosmology, for examples. So my project was to model a light curve of a supernova with Phoenix. So that's something that Phoenix obviously could not do, because now we have to include time dependence, a light curve, the emission changes, of course. In Phoenix normally does not assume time dependence, so it just says everything is constant in time. Usually for a star, it does not change for millions of years, so it's absolutely fine. Now for modeling a light curve of a supernova, I had to include the time dependence. And I did this just by taking a look at the energy. So there are basically three things that change the energy in the envelope of an expanding type 1a supernova. One is, of course, a change in every layer by absorption and emission of radiation from the other layers or from the radiation field. That is very simple, but it's the most complex, actually, but for me it's very simple because Phoenix does it already. So I'll just solve the radiative transfer, and it gives me as a result how much energy change will there be in a time step due to the absorption or emission of radiation. Then you have an energy loss, of course, by expansion, which is also relatively simple. It's just an adiabatic expansion, so you reduce the energy from one time step to the next. You know exactly how your envelope is expanding. And then there is the real energy source of a type 1a supernova. Without the radiative decay, you would actually not really see a supernova. So what powers the light curve is the energy from the radiative decay of nickel to cobalt and then to iron. So when the supernova explodes, it produces a lot of nickel, and then within a few days that decays to cobalt, and then it decays to iron, which is then stable. And this emission of energy is added to the envelope and actually causes then the rise of the light curve and then how the light curve drops. So I included this as well. Good thing is, if you know the result after the explosion, so how much nickel you have, with basic physics you know exactly how much energy you have to add. And that was then my work in the PhD. So this is the result. This is the light curve in the V band. There have always been problems in the I band. So this is the original model that I calculated. But if you look into the literature, other people that try to model the light curves in the infrared had the same problem, and that's probably because in the later phases the atmosphere starts to get more and more transparent. You have energy effects, and that then causes. So what I did was a correction factor, another parameter that I added to my code, but with that you could then actually also model the light curve of supernova. Okay, now so that was what I did in Hamburg. Yeah?
So does that mean that you have one spectrum per each? Can you go back? So one spectrum for each of these symbols.
So the symbols are observations of supernovae, and but my model has also in each time step, of course, it has a spectrum. So that's also very computationally demanding because you have to solve the radiative transfer in every point of these.
So you not only can compare with the magnitude, but the evolution of the spectrum.
Yeah, exactly. Yeah. Actually, I have also published a paper where we could identify which is the feature that causes the second rise. So in the infrared, you usually have a secondary maximum. So you can really identify the line in the theoretical spectra that caused the rise of the secondary maximum. Okay, so after that I left Hamburg, and I also forgot about my code of calculating light curves of supernovae. I started to work in Guanajuato, and there I usually modeled stars. I was working with Klaus-Peter Schröder, who works with low mass stars, with giants. So I started to work a bit on that, but that was just modeling normal, let's say, normal stars, also stars with the Phoenix code, and I really forgot a bit about my code. Then Klaus-Peter, he also works with chromospheres, and he was always telling me, try to model the chromospheres, please. I said, oh, that's really difficult, and I said, no, I don't know. Okay. But then I really start to do it, and I'll come to that later. So just quick introduction to chromospheres. I'm not really an expert, but the chromosphere is above the photosphere. So Phoenix does not model it. It cannot do it. The chromosphere is related to stellar activity. So you have all the spots, flares, what you see on the sun, has an effect on the chromosphere. And you observe it also in the spectrum of the sun. So here comes the star, the temperature drops. Here's the photosphere, the temperature usually drops, and it should drop as well. But if you take a look at the chromosphere, you see that after a minimum, the temperature actually rises again in the chromosphere. So the idea is to, of course, get this rise in the chromosphere, the temperature, and of course see if that has then an effect on the spectrum and compare it to observations. So, taking a look at observations, there are a few lines which are kind of indicators of the chromosphere, or which are affected by the chromosphere. The most known is, of course, the calcium H and K lines, which are blue going towards the UV, and you see that normally it has a very broad absorption vector. So this is here, if you have the quiet sun, you have a bit of emission, but very little. If you go into a plate to active region, you see that there is actually a emission peak in that line of the H and K line. You also have an effect on magnesium, for example. So these are two magnesium lines which are really in the UV, so a bit difficult to observe. You also see that if you have an active star, that the emission. And the more active the star, so if you take a look at other stars, you see that higher is the rise actually of this emission feature. You hardly see it, but you can also get some effect in the hydrogen lines. It has also an effect in the radio. It increases a bit the emission if you have activity in the star. Okay, so that's the observational part. So what are the problems that we have with chromosphere? First of all, we know that the temperature starts to increase, but still, we have some ideas, but we really do not know why. What is actually happening there? So where does the energy in the chromosphere come from? It obviously cannot come really directly from radiation because it's optically thin. The radiation just passes through it. There's no way that you can heat the chromosphere just by radiation. So there must be other factors. One idea is that it's a magnetic field. So we know that the magnetic fields, especially you can see it in where you have spots, active region, that the magnetic fields go into the chromosphere. So the idea is that somehow by interacting with ions, it starts to heat the chromosphere like this. Other ideas are that there are acoustic or seismic waves that travel from the photosphere or from deeper into the chromosphere or in corona, dissipate there, and therefore take up the energy. So at one point when Klaus said to me, please model the chromospheres, and I said, oh, that's too complicated, I don't want to do this. I remember what I did. So we are talking about energy. So I remember what I did in my PhD with energy. So I applied my supernova code to chromospheres. And it's actually much easier than modeling supernova because, so what I did was, what we want to have is, of course, we want to have the rise again in the chromosphere and the corona, but that's too thin, we're not going to do this, but at least the chromosphere. So we need to have the increase in the temperature in the chromosphere. And we know that somehow there's energy put into the chromosphere that causes exactly this. So my idea was, well, let's apply the code that I wrote for the S supernova light curves to chromospheres. The idea is the following. First of all, it's much simpler because there's no expansion, so one term already goes away. Again, the second term, which was the absorption and emission of radiation, Phoenix does it for me. So I just need an energy source, and what I did was just, okay, let's just say somehow, since nobody really has an idea how it works, somehow there's energy put into the certain layers of the chromosphere, and let's see what happens. So I let my code run. Of course, what you do is then you have the structure of your atmosphere. In the chromosphere, you say, okay, in these layers, I put some additional energy, and then I let my code run until, some time steps, until there's an equilibrium reached, and you really have, hopefully, a temperature rise in the chromosphere. And here is then so this is how you start. You start with the photosphere. So here is that's really the photosphere. And then usually in Phoenix you have the drop of the temperature as you go higher up. So I let then the code run. Good things about time dependence is that you can do little movies. So what you see here is that immediately it rises. And you see a few effects. You have back warming, so the energy that is here also radiates in this direction, so back on towards the star, and it starts to increase as well parts of the higher parts of the atmosphere. And this is then the final result, which I think is actually not that bad. So you have the temperature drop, and then to the minimum, which used to be somewhere around 4,000 Kelvin, and then it goes up. And stays then constant. And corona goes somewhere there that I'm not really interested in. So it seems to work. Let's take a look at the spectrum. This is again, this is actually, so you see here, these are two things that I compared. So you see really that in the calcium, this is the K I think, you have really a rise, so the emission, it's not, the profile is not really good. There are still a few problems that we need to solve, but you have a rise of the emission in the calcium line actually. And then this is what Fiber was interested in the radio. So this is without the chromosphere. And with the chromosphere, so you have a little bit more emission in the radio with the code. So I have to mention, Phoenix does not really do radio, so this is just like the Planck dropping down in the radio, but still you see the effect of the chromosphere that there is a small rise in the radio of the star. Okay. Okay, so first of all, it works, but there are still a lot of problems that I have. So the principle, it works. First of all, it's computationally very demanding because again you have to do time steps. And since we are in the chromosphere, the assumption of LTE is not really good. So you have to do non-LTE, at least for the most abundant elements, and of course for calcium, where you are looking at magnesium as well, where you have the emission, but to be honest, it should be all of the elements, and that's something that is very demanding to do this. Also, what I did was just, okay, I said, okay, those two layers, I'll put some energy in there and see what happens. But I have no idea, is it the right amount of energy? Is it really in those layers? Is it the same energy in every layer? Does it increase? Does it decrease? Even if you take a look into the literature about how would be the energy distribution of different models that do the simulation of chromospheres and the heating of the chromospheres dynamically, they do not really give you that. Also, so you have not really an idea, so this is playing around with a lot of parameters, trying to fit the temperature structure, but this is the next point. So how does the temperature structure look like? We actually do not really have an idea. So no one has gone to the chromosphere and measured everywhere exactly the temperature. It has been done by observations of specific lines that have emission due to the temperature change in the chromosphere. So it's, again, there are several publications that give you a difference. One say that the minimum is at 4,000, so it's a bit lower, it's a bit higher. The temperature in the chromosphere varies also with a few hundred Kelvin. So I'm trying to fit something where I do not really know how much energy I have to put in there, and without really knowing what to fit exactly, you know? So that is still work in progress, trying to figure out a bit and play around a bit with the parameters, but that's actually a lot of work. And I think the main problem is actually the energy effects, trying to include this. So I really need a supercomputer to do this. And again, now if you can play around with all of these parameters, you have to do a lot of models trying to see how all of this really affects the temperature structure and the emission of the lines. But anyway, in principle, it works. Okay, just a quick summary. I think maybe that's good in time. Yep. So, my idea here was, first of all, to present the Phoenix code, what it can do, give you a basic idea about all the physics that is included in there. The good thing is you get a theoretical spectrum that you then can compare to your observations, and with that you get a better idea of what your object of interest really looks like. So there's a variety of applications that you can use. There is the 3D radiative framework, which is still under development. And as I said, my last thing that I did was trying to include the modeling of chromospheres. There was actually a module in Phoenix that modeled the chromospheres before, but it was not self-consistent. So what they did was just, okay, there's a temperature rise, and they just forced Phoenix to accept the temperature rise and then take a look at the spectrum. That causes a lot of crashes of the code because it was not physically consistent and so on. So my approach now is much better, but again, now I have 3 parameters which I can play around with. Okay, then if you're interested in the Phoenix code, it's not public, that's the bad news, but there are a lot of models which are public, which you can access, normal stars, given for given temperatures and gravities and so on. You can download them and get also in the spectra. Of course, you can always get, if you want something very specific, it's possible by collaborations with people that work with the code. It could be me, for example. So if you're interested in the Phoenix code, feel free to write me or even to directly to Klaus at Peter Auschel. So he's usually very willing to model some of, but he does not give the code. No? Also, it's very difficult to use the code, so it's a good idea to have someone who knows how to use the code. And with that, I'm at the end. Thank you very much.
Thank you, Dennis. We have questions.
Yes, thank you for your talk. I was wondering about the presence of a stellar wind in your chromosphere models. How do you include it? by the expansion of the envelopes? Or?
So right now it's not included, the wind. It's a good point. I don't know if, I have no idea how the module for the winds actually works. But yeah, it would be an idea to see if that has an effect as well but right now I'm not including any wind in my model.
Okay. You have a question?
I have two questions. In the 3D framework for the RT, which method do you use for that?
To solve the radiative transfer, it's basically the same equation that I gave you at the beginning. So it's really following characteristics through the whole volume of the star, of the object. So it's nothing like Monte Carlo or something. It's really solving the radiative transfer, going from one voxel to the next, and how it's the change of the radiation intensity.
And the volume through which the ray passes, it's a box? Or it's
exactly, it's like a box. So you divide your star into millions of boxes, and then you have to solve, that's the complex part, you have to solve. Of course, every ray can go into different directions through all your voxel grids, so you have to be careful a bit to hit every voxel in every direction, and you have to do this for every wavelength, so that's why it's computation also so demanding.
And for each box, you have like you solve the state equation for each box of all your star?
Well, that's what you actually need to do. You need, for every voxel, you need the physical properties, the opacities, and wavelength point, and so on. This is still not possible. So far, what you do is, I don't know, constant temperature or a given temperature in every voxel, a given density, and then solve the radiative transfer. That's as far as you can go so far.
Yeah, just I have a similar work in my PhD. So one approach we did is to not solve all the cubes, but solve like certain cubes with certain parameters, and we assume that in other stars maybe there are similar cubes.
Okay.
And we only, let's say from all the stars, we only solve one cube. For example, if you have a homogeneous surface or a homogeneous atmosphere, and maybe that could reduce a lot of calculation.
It would, exactly, yeah.
Or maybe not solve one cube or box, but 10 or 100 certain specific boxes.
Yeah, so it's a good idea. I will talk to Peter Hauscher about that. I know him, so he usually is very, wants to do everything very correctly. Yeah. So I guess he will say, no, you have to do this exactly in every box.
I think if you could
for applications, it would be good too.
Yeah, I think you could like give a statistical like reason that you can do this because let's say you can repeat some boxes, and you can give a statistical reason for that.
Exactly. Even more when you have symmetries, no? Some symmetries, you have the same voxels for.
And actually, in our model, we only grab the box and rotate it to calculate the path of radiation. And we don't actually like put it in on a surface, but only rotate it. And that also makes a lot of reducing in the calculation.
Yeah, that's true.
There's a lot of things you can do. Computation.
Okay, yeah, thanks.
Yeah, so regarding the output spectra of massive stars, how do they compare with other codes like T-Losty? I've been using T-Losty for some, and also some colleagues, so I'm wondering if I should also try.
So what I know is that for massive stars, it's not that good. So I guess a code that is specifically designed for massive stars would be probably better than than Phoenix. So going above 10,000 Kelvin effective temperature, Phoenix does not include all the physics as far as I know, because I think there's no one who really works that uses Phoenix and works with massive stars. Most of the people are more in going to the lower temperature range.
Jesus, you have a question?
It was related to us.
Yeah.
Quick question, you mentioned on one slide, you can apply this to neutron star atmospheres. So I'm wondering, do you have include strong magnetic field effects?
Magnetic fields it does not include. It has there was one PhD student who rewrote the code, including general relativity. With that, trying to apply it to neutron stars as an example. So magnetic fields are not included at all in the code.
Okay.
We have one question on Zoom, Miguel Chavez.
Yeah, thank you, Dennis. Nice to meet you.
Hi.
I have a comment and a question. The comment is, can you hear me?
Yes, I can hear you.
Okay. The comment is that I'm very glad to see that someone is trying to model also the temperature structure of the atmospheres, even the upper atmospheres, because that will have very important implications, for example, in understanding the atmospheres of exoplanets. If you go to the ultraviolet, the mid-ultraviolet. And the question is, do you have plans to improve also the atomic and molecular opacities? Because that also has important implications in many aspects.
Yes, that's true. Right now, not really. So I know that Peter Hauschel is trying to improve collecting all the data available to increase our database of atomic and molecular lines, but that's more something that he is doing. So I was not really planning on going into that. But maybe you're right. The data of atomic lines is really a problem. No, we have not really an idea how good they are, and Phoenix just uses what is available and assuming that it's the way it is. But for some lines, one may get into this and trying to correct the data there.
Mm-hmm. Yeah, thank you. In fact, the point is that let's say in the ultraviolet, which is full of lines, the atomic and molecular opacities are a big problem. And as once said by one of these colleagues, famous in stellar atmospheres, Bob Kurux, he said something like the atomic parameters are okay within a factor of 1,000. So that's something that has to be improved. And we are working here at INAOE on that line, but we are not improving the temperature structure. So I think we will contact you and see whether we can do something together and improve everything at once. Thank you.
Yeah, sounds good. Okay.
One more question? Okay, Martin.
Sorry. A little question. Which are the time steps in your evolution of the chromosphere, and which is the total time of the evolution in that?
It was about seconds or something.
1 second.
A few seconds. And so within a few seconds, the whole structure is adapted. So it should be something, to the time scale more or less of the star.
Okay, let's thank our speaker.